Hello, Unite. I'm going to take you through our little assessment task so you can check up on how well you did. Okay, question 1. We're ticking the check boxes of the materials that are electrical conductors. Remember that metals are electrical conductors. So let's tick the metals. Copper and rubber and plastic are not metal. Aluminium foil is metal. And steel is metal down the bottom. Our other exception, not our exception, but our other answer is salt water, because that contains sodium and chloride ions, so things with charges, and they can move throughout the water. So salt water is also an electrical conductor. Okay, the insulators are the opposite things. Things like rubber, plastic, and paper and wool. And one thing these have in common, you might not think so much about the plastic, but the wood, the wool, wood would be on that list too. The wool, paper, and rubber are all made from living things, natural things. So wool from sheep, paper from trees, rubber also from trees as well, can be, or we can make it synthetically. All natural things. And natural things don't tend to transmit electrons. Plastic also, most plastics are insulators as well. Okay. Transparent. Okay. So these questions, you'll notice the three next ones are all about how light can travel or not travel through material. So remember with transparent lets through all light. Okay, so all light is going all the way through the material. Okay, and remember that translucent means that some of the light is going through the material. So let's say that these are maybe different colors. You're getting two of them coming through, but one of them being absorbed. Okay, and then opaque is no light is making its way through. Okay, so transparent is, well, glass is transparent, so hopefully you got that. And air is also transparent. Hopefully you got that. It lets all light through. Okay, let's pick out the translucent ones. Okay, now classic one that I put in there was sunglasses lenses. Sunglass lens lets through some light, but it doesn't let through all of the light. Okay, it blocks some of them to protect your eyes. Also, the other one that we're looking for there is a stocking, a nylon stocking. It lets through some of the light, but not all of it. Some of it is blocked. Okay. Now, the opaque things block all of the light, so hopefully you can pick out the brick. Can't see through a brick. An apple. No light makes it through an apple. And also a piece of iron. No light makes it through a piece of iron. Okay. So, electrical symbols. Hopefully you studied well. This one here is an ammeter. It measures current in amps. This big V is a voltmeter. It measures voltage in volts. And this one here, we accepted a few answers. So you could have used battery or transformer, which we use in the classroom, or battery pack, any of those. There was a few others that we accepted, power source, stuff like that. Any of those variations we all accepted. And the next one here, the circle with a cross, is a bulb, or a light bulb, or a lamp, or any of those kind of variations, as long as we can tell you that you're talking about one of those things that light up. When electricity runs through it, we gave you the mark there. Okay, the next symbol was a wire. So we accepted a few variations there, like lead and stuff like that. Next symbol was a switch. A few people noticed that was an open switch, which was good, but we accepted stuff. We accepted switch. And a couple of little variations there. An instrument to measure current is, I just talked about that up here. It's the ammeter, okay? A current meter We did not accept. The proper name is an ammeter. It's not a voltmeter, and it's not an ohm meter too. Okay, electrical current is a flow of electrons, not protons, not atoms, not neutrons. And refraction, when it comes to light, remember, refraction is when light travels through different materials, or the fancy word different mediums, it changes speed, okay? And because of that change of speed and a property of the light, it can change direction. But the changing of the direction is due to the change in speed. So you should have put down this top one here. Let me go back to my pen. Change in speed. It's not the bending of the light. The bending of the light is the result of it, so not that one. It's definitely not the bouncing when they hit the mirror. That's reflection. And the bouncing back of light rays when they hit a transparent object is also some reflection as well. Which property of light allows you to see yourself in the mirror? Not many people, I don't think I marked anyone wrong for this one. It was reflection. Okay, you see your reflection in a mirror. Okay, the next few questions refer to this circuit diagram. A, B, C, D, E, light bulbs. That's another symbol for a light bulb. I think everyone recognised that, which was good. Excuse me. So which two or more of the light globes are connected in series with globe A? Okay, so here's globe A. The ones that are still in the same line as A are B and C. So this one's B and C. So we only accepted any variation of B and C, okay? If you just mentioned B, you wouldn't get the mark. Or if you just mentioned C, you wouldn't get the mark. Alright, let me erase that. I'm going to scribble all over it. Two or more lights that are connected in parallel with globe A. Okay, parallel means they're on their own separate line, and that is the other globes D and E. Okay, they're on a different line to globe, a different part of the circuit, or a different circuit. Well, there's not a different circuit. There's got some shared parts, but it's on its own parallel with A. So it's D and E, and again, you needed the 2 to get the mark. Okay, if the switch in the circuit was opened, the switch is here between D and E, which of the light globes would stop glowing? Well, you're putting a break in the circuit here. So this circuit here no longer works, okay? But you have to recognize in parallel that we've got another circuit here. This circuit here is still complete, okay? So breaking that switch really breaks that lower circuit, or the red circuit that I've drawn in there, so only D and E would stop glowing. Okay, so again you needed both of those. If the filament in globe B was to break, which lights would stop glowing? Okay, let me erase my scribble. So B's out, and the filament is part of the circuit. So if the filament breaks, this inner circuit now will not work, but this outer circuit will still work, okay? So B will definitely go out, and a few people picked up that globe B would go out. Yes, that's good. We didn't really give a point for that though. We wanted to see some variation of A and C, okay? If you gave A, B and C, you still got the mark, of course. It was good that you picked up, of course, that B would go out. But we're looking for both A and C to get that mark there. Okay, question 20. The voltage across globe C was measured at 4 volts. Let me just erase my scribble. Okay, so globe C, 4 volts. I'm going to write it above it. Okay, what is the voltage across globe A? So remember, in parallel circuits, that the voltage will go down however many paths, okay? So the voltage is conserved for each path, okay? But we have, in this path, 3 components. So the full voltage goes down this first path here, but it's shared between 3 of them. And the full voltage also goes down this second path, and it's shared between those two globes. And it's shared equally, which these globes are all equal. So it would mean that all A, B, and C would all have 4 volts. Okay? So if globe C measured 4 volts, globe A would also measure 4 volts across it as well. If the voltage across globe C was measured to be 4, what is the voltage across this power supply? Okay, look, I've drawn the 4 volts. So the full voltage went down this first path here. It was shared equally among 3 and each got 4 volts. That equals 12 volts going down that path. Okay, so to be 12 volts going down this path, sorry, I should draw it there, and 12 volts going down that path there as well. Okay, because voltage is conserved for each path. It's shared within a path, but each path gets the same voltage. Okay, so the power supply gave 12 volts. If the voltage across globe C was 4 volts, what is the voltage across globe E? Okay, as I just said, each path gets their 12 volts. Each path gets the full voltage. So this path here gets 12 volts and it's shared between 2 equally. So that means each globe gets 6 volts. So globe E gets 6 volts. Okay, hopefully you put your units in there. We tended to work with those questions. I think with those 3 of them there, that if you did not put any units there, you could only get a maximum of 1 point. Okay, so I accepted capital V, or the full word for volts. I think I accepted a lowercase v, but I wrote a comment there too. Okay, so please, when you're talking about a measurement in science, use your units, because I'm going to do the classic thing and come back to you and go, for what? For elephants? For VW cars? What are you talking about? Okay, be specific. 23, back to a multiple choice. This one sorted a few people out. Okay, here we have a voltmeter, and there's 2 settings. There's this setting here, and there's this setting here. So that's your negative, and these are both positives. Okay, but there's 2 scales here. There's and you'll notice down the bottom, a 0 to 2 scale. And that happens when you put a lead into this one that's labeled 2. And let's change color. There's also, when you put a lead into 20, you read it from the 0 to 20 scale. So look at this. Our wire's going into the 20, so we read it on the 0 to 20 scale, the upper scale. Okay, now let's look where it lands. It's landing on this second one, okay, in between the 5 and the 10. Okay, so how many divisions are there between 5 and 10? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 divisions between 5 and 10. Okay, so there's 10 divisions dividing 5 volts. So each division is 0.5 of a volt, or half a volt. Okay, so if it's 2 divisions past 5, it's 2 halves past 5. 2 halves equals 1, so it's 1 volt past 5. 5 plus 1 equals 6 volts. Okay, a few people tripped up on that one. Okay, so look at the scale. Okay, where it's going into 20. Find the right scale, and even then I still had a few people put in 5.2. That would only be 5.2 if the 10 was 6, but it's not. That's not a 6, it's a 10. So be mindful of your scales and use the technique that I use there. Okay, count how many divisions, look at what differs those divisions by. So we saw it differs by 5 volts. 10 divisions per 5 volts, that makes 1 division for a half volt. Okay, 2 divisions past 5 gives me 2 halves past 5, which gives me 6. Most people didn't have trouble on the I one as well, the I one with the lens. So the short-sightedness, just like I have, and why I wear glasses, is I want to be figure 2 because then my eyesight's not blurry. Okay, so the lens is to refract the light rays. Okay, not to absorb, because then I'd be blind. You'd have totally black glasses. They wouldn't even work as sunglasses. Not to reflect, not mirrored glasses, totally mirrored, and not to scatter as well, to refract, okay? All right, let's work through this one, okay? Circuit diagram below, our voltmeters are labelled V and a number, and our ammeters are labelled A and then a number. Voltmeter 3, this one down here across this globe, measured 12 volts, written there, and ammeter 3 measured 4 amps. So what you needed to do in this question is remember your rules, okay, about how voltage goes around. And you've also got to recognize that we've got a parallel circuit. So we've got two paths here, okay? Should I highlight them in different colors? That might work well. Hold down my highlighter. Oh, I can get different highlights. All right, so we've got this path here. This is one circuit. And we've also got, let's do it in green. We've also got this path here, okay? So we've got a parallel circuit, and remember, for parallel circuits, the voltage is conserved, which means that each path gets the voltage, and current is shared, okay? So, we're starting off with current because it's asking us for the reading on the ammeters. Okay, so look, 1, 2, 4. We've got the ammeter reading 3, and that was 4 amps. Okay, so current is shared. So ammeter 3 down the bottom there is showing that that path got 4 amps. So that path got 4 amps, and this ammeter here, ammeter 4, is in series with it. Okay. Ammeters in series will measure the same current. So this one here, let me go back to my pen, will also be 4 amps. Okay. So that path got 4 amps. So that means that this path after this point will also read 4 amps. Okay. So ammeter 2 would read 4 amps. And any other ammeters that you put along this line between here and here would also measure 4 amps. But as soon as they join back together over this side, the current is going to be not shared at all. It's going to be I'm going to use the word put back together. Oh, electricians are probably going to hate me for saying that, but it's a good way to think about it. The two paths are shared here, so we're going to get both the currents. So that one's going to be 8 amps, and the one that's back here before they split are also going to be 8 amps. Okay, so ammeter 1, looking at my diagram, it's right up the top, so it's 8 amps. Ammeter 2 is in that middle path, so it's got that 4 amps. And ammeter 4 is down the bottom there, so it's also getting 4 amps. Okay, I didn't ask about ammeter 5. Oh well. Let's think about voltage. Okay, should I change colours? That might help. I'll change to purple. Our voltage that we're given is, this globe is 12 volts. Okay. So remember, voltage is conserved, so each path is getting the same voltage. Okay. But multiple globes on the same path have to share that voltage. Okay, so that 12 volts down the bottom on that globe with voltage 3, the voltage 4, this one to the left of it, because it's on the same path, it must have shared the voltage with. So it's also 12 volts. Okay, they're the only two components on the path, so that means 24 volts must have been going around that path. Okay, and that means that path must have also had 24 volts. Okay, now this first path, the orange path that I highlighted, only had one globe, so it got the full 24 volts. Okay, so the voltage must have been given out by whatever this power supply is, must be 24 volts. Okay. So voltmeter 1, question 28 here, not question 29. So the voltmeter 1, let's find it. It was, up the top with the power supply. So that's 24 volts. And voltmeter 2 is in the middle there, that one globe on the path. So that's also 24 volts. And voltmeter 4 down the bottom had 12 volts. All right. Okay, here's the questions that I made. Making terrible circuits at school. I had a bit of fun going, what can we do wrong? So this circuit here, in question 31, not question 32, question 31, this one here, you'll notice it doesn't form a complete circuit. I might get a brighter color there, like orange. It's not a complete circuit because it's not a complete circle. What you could do, and most people got, was from the negative DC port, connect up that positive terminal for that globe there. Okay? So connecting the positive of that second globe up to the negative of the DC globe would complete the circuit. That's what we're looking for there to get the full 2 points. Okay, this one here we've got, if you zoom in, what have we got? We've got an ammeter. Okay, and the rules for connecting up an ammeter is that you connect it up in series. Okay, is it in series? Yes. So it is in series. So that's good. In my horrible orange writing there. So it is in series. Okay, but have a look at the reading. It's negative there. Something's wrong. And have a look at how I put these plugs in. Okay, when you plug in an ammeter, or when you plug in a voltmeter, you need a plug in the negative and a plug in the positive. Now remember, you can get ammeters and voltmeters sometimes with 2 scales in them, and you'll have two positive plugs for it. Oops, sorry, let's get rid of that. 2 positive plugs for it, and have a look here. I've got both of them in the positive, and I should have one of them in the negative. Okay, so a few people got this. Okay, so it's not working properly because both of the wires are in the positive, whereas we should have one in a positive and one in a negative. Now, a few people said which positive should be in. We didn't really mind there if you wanted to go into a bit more detail, but what we're looking there for the full 2 marks is that you recognize that both of those plugs are going into the positives of the ammeter, and that one of them should go into the negative. Okay. Okay, this question here. A student was measuring the current of the circuit. Okay, identify the method why it's incorrect and how would you fix it. Okay, here's the ammeter. You use an ammeter to measure a current, and what do? You wire it in series. Okay, so this one was wired incorrectly in series, but look at this. This one here is forming its own little parallel circuit around that globe. That's not how you wire an ammeter. That's how you wire a voltmeter. Okay, so to recognize what was wrong there, you'd have to say something along the lines of the ammeter was not measuring the current of the circuit because it was not wired in series in the circuit. It was wired in parallel with the globe. How would you fix it? We accepted any answer that would show that you're now wiring it in series with the circuit. All right, next question. What's wrong with this one? Okay, have a look at the question. The student measured the voltage of this circuit. Okay, to measure the voltage of the circuit, you got to measure the voltage across the output. Okay, definitely haven't measured there. Okay, and I've deliberately put the voltmeter in series rather than in parallel. Remember, voltmeters form their own little parallel circuit around what you're trying to measure. So if you're saying that you want to measure the voltage across that globe, you make a little parallel circuit across the globe. If you're saying you want to measure the voltage of the circuit, you measure the voltage across the power supply. Okay, but here I've just wired it in like it's in series. So most people recognize this. A few people got it that you'd need to wire it in series across the power supply is the word that I'm looking for. Okay, this next question here. I'm measuring the voltage across this globe. Okay, that's good. What is wrong here? Well, I've made my own little parallel circuit, which is good. So there's been an improvement. I've made my own little parallel circuit across the globe. All good. Okay. Now, I've got a plug in the negative and a plug in the positive, which is great. But have a look. It's going... the actual meter is going negative. And remember from the videos that we saw, when it's going negative, what you need to do is just change the polarity, just swap the plugs over. Okay, so here we just need to recognize that you had the negative and positive on the voltmeter around the wrong way, and you just needed to swap those over. Okay. This one here didn't trip up as many people as what I thought, which is really good, okay? It is the same question as before, so a lot of people talked about how the voltmeter, the plugs needed to swap around, but the main thing why this circuit was really not working was that the switch on the power supply was off. And you may laugh at that, but all the time during a practical, I get called over, "Sir, this is not working." And I flick the switch or flick the power switch on the transformer as well. So that's why I added that question in there. Okay, this last part all has to do with graphing. And I actually had a few more problems than I'd hoped for with this one, okay? So here, 4 students investigated the change in current flow through a lamp using different batteries. Okay, so they applied different battery voltages, if I can talk properly, and they measured the current. And so they used an ammeter to connect in series, and a voltmeter was connected in parallel to the globe or the lamp. And the results we tabulated here, and the students didn't get any data for 6 or 12 volts, which is fine. Okay, so 4 students produced these 4 graphs. Okay, now this one asks you which one is the correct one, and the other one asks you for one of the graphs that you didn't select, why are they wrong? What I'm going to do to answer both of them is talk through what's wrong with them and then point out what's right with the one. So looking at graph A here, the first thing that is wrong is your trend line is a line of best fit. I have not got one line here. I've got 1, 2, 3, 4. I've got 4 lines of best fit, okay? Single line of best fit. Okay, now adding to that, it can be a curved line. It needs to be a smooth curved line though. It can be a straight line with a ruler, and here we have a straight line relationship. On other occasions you'll notice a curvy trend, but you definitely do not do a dot-to-dot pattern. Okay, I had a lot of people do that in the past. Science and in the real world, we do not get dot-to-dot relationships. Now, economics and some of the maths graphs could do that and jump up and down, but very rarely will we use a dot-to-dot graph in science at all. Okay, we go for single trend lines, and that's how, because nature's very mathematical, it gives us a nice mathematical relationship. Now, other than that, graph A is quite good. Let me erase what I've done. Okay, the good things that they did is they chose a good scale for their x-axis that takes up the majority of the space. Okay, that graph, the graph data takes up the majority of the space. The other good thing that they did is these data points. Okay, I can clearly see as a scientist where they've actually got data and where the trend line is between them. Okay, not the correct trend line, but let's not go there. Okay, I can actually see the data points. So they've used bigger crosses, or you could use bigger dots or little triangles to show here's where my data actually is. So they've set a good scale, they've put their numbers all across. Now you don't need to put 1, 2, 3, 4, 5, 6. They could have gone 2, 4, 6, 8, 10 to leave it a bit busy. Either one is fine. Okay, but they've taken up the majority of the space. They've put their data points in. The main thing that graph A did wrong is this dot-to-dot point lines of best fit. Okay? Alright. Graph B. Okay? as I was just saying, a graph should take up the majority of the plot area. This does not do that. That's terrible, okay? That will lose you marks. And it is quite important because if you have all your data points gathered up like this, it may seem like it's a straight line. But if you expand it all out, you may notice that it might not be quite a straight line. It might be a slight curve. And, I mean, just on a tangent here, I gave my Year 11s a graph just like this in a recent assessment task where some people didn't take up the entire plot area and presumed that there was a linear relationship between two things. But if they'd taken up the whole plot area, they would have seen the slight curve and they would have seen, it's not a linear. So be careful. It happens. Okay. So here, and they've given clear data points, which is good. Oh, I was trying to highlight them. They've given one trend line. Okay, it is a straight trend line, which is pretty good. It goes close to as many points as possible. It's not too bad, but it's not quite there because they've extended the trend line and they've included something else in here. I'll change colors. Look at this. They've gone for like a 0, 0 data point. They've added in a data point at 0, 0. Now, there's a few times in mathematics where, for some reason, I don't know why, we don't really hit it in science, they say join the graph up to 0, 0, and it's only in a few rare instances. It's not in the majority of mathematic graphs. Now, in science, we only include points that were actually measured, okay? Did we have 0 volts give 0 current? No, that's not in our data set. So this should not be there. And for that, if that wasn't there, a better trend line would be something like this. Even though I'm not using a ruler, but I can hold down and get a straighter line. It doesn't work through my scribble. Okay, so putting that 0, 0 in is not so good, and extending or extrapolating that line down, not good at all. So graph B, not a good X scale, and they've added a data point in there. Okay, graph D, no trend line. Okay, no trend line, and also I'm just having a mental blank there. This X graph, it needs to be taken out as well. No trend line. All right, let's take it to here, graph C. What I like about this graph is it takes up the majority of space. Tick. I can see the clear data points. Okay. I can see a trend line here that's a single line. Okay, that's not a dot-to-dot point. It doesn't go through every data point. You do not need to do that, okay? It goes close to as many data points as possible. Okay, notice how it kind of goes through 3 of them, the top and the bottom and the middle really well, but this one's a little bit under, but this one's a little bit above, and that's okay. You want a kind of a balance between them, okay? So your ideal when you're doing a trend line and you think it's linear and it's kind of showing a straight line is that you want roughly the same amount above as below and by the same distances, okay? So that's a good trend line. They haven't extended it past, which is really good. So the fancy word for that is extrapolate. They haven't extrapolated their data or taken it beyond where their data has gone. And this within here, which is called interpolation, they've done a nice linear trend there, okay? So the one that makes me most happy and the one that will get full marks is graph C, okay? That one there had no problems at all, okay? And again, with these numbers, you don't need to number every line there. They could have gone 2, 4, 6, 8, 10, you know. As long as you have some of the numbers in there, you're fine. You don't need to number them all. All right. I hope that was helpful, and I'll talk to you next time.